Well, today we're going to talk about properties of logarithms. And I think these are great fun. And working with logarithms is a lot like solving puzzles, which I enjoy doing. And I think you'll enjoy these too. First of all, why were logarithms created? What are they? We talked about this last time. Logarithms are exponents, and therefore they follow the laws of exponents. And why were they created? Well, way back in the 1600s and the 1500s, astronomers were looking at the sky and they were trying to figure out whether or not it was true that, in fact, the Earth was the center of the universe, as was maintained by the church. And I guess you know the first person to make a major challenge to that was Copernicus, and he was reviled by the church thereafter. And then there was a guy named Galileo who came along and, of all things, used logarithms to help him prove that the Earth was not the center of the universe, and in fact the sun was the center of the solar system, and that wasn't even necessarily the center of the universe. So the church deemed logarithms tools of the devil. So I hope you won't regard them that way, but we will be dealing with these tools and having some fun with them, I think. As I say, they're like puzzles to me, and I hope you find them that way too. So what did logarithms do, and why would Galileo use them? Well, this guy named John Napier, back in the 1600s, saw that these astronomers were spending a lot of time multiplying these astronomical figures together. And one guy said that Napier's logarithms lengthened the life of an astronomer threefold. In other words, people were getting 3 times the accomplishment as an astronomer because they were no longer having to multiply these huge astronomical numbers together. Well, how is that? Because logarithms, you're able, instead of multiplying, you add the 2 numbers together. Then you go to another table and you look at the result of your addition and you work backwards and you can figure out what the product of the original 2 numbers you were multiplying is. So it was a tremendous benefit to astronomers. So let's take the very basic concept of logarithms, and that is that log xy equals log x plus log y. Now you can see how this relates to what I was saying. When you have the product here, and here you just add the logs of those 2 numbers together. When you get that result, then that is the log of xy. If you can look in a table, and by the way, your calculator, as amazing as it is, has all of the logarithm tables that I used to carry around when I was in high school. Half of my math book was log tables. And all of that is stored in your calculator's memory. So you guys have a tremendous advantage and don't have to carry around that book of logarithms. Anyway, let's see how this would apply to a simple example. If we had the log of 6, then that would be equal to the log of 2 plus the log of 3, wouldn't it? That would just be an example. Obviously, the log of 6 plus the log of 1 would equal the log of 6. So the log of 1 that's going to be also true. And by the way, you can check this in your calculator. So the log of 1 must be 0, eh? Because if that's added to the log of 6 and it equals the log of 6, there we go. It must be equal to 0. All right. What else do we have? This is a basic truth that you're going to need to know. You work either way with this. What about the log? How can it help us in division? If we have x over y, then that equals log x minus log y. So the other example that would be similar here, log of 6 equals the log of, let's say, 12 minus log 2. And you can check that in your calculator. By the way, in your calculator, it'll come up log when you press the log button, and then it will have a little space down here, which is the base. And you can cursor over that, by moving your cursor to the right and going to the argument. You remember that these are log and the base and then the argument. And what does that equal? That equals an exponent. Okay, and in your calculator, in the Inspire, it'll have a little thing here where this will be flashing, but you can cursor over that. Remember, when you have just log, like we've written log 12, that is an understood base 10. This is understood base 10. And by the way, this could be anything. This could be log base 7, 6 equals log base 7, 12 minus log base 7, 2. You have to keep the same base, though, when you're making those statements. All right, let's look at one other basic truth, and that is that x log y, x times log y equals log y to the x power. In other words, this x that's out in front becomes the exponent of the argument. And you need to know this and be able to work back and forth with this truth. Depending on your problem, it's sometimes better to pull it out front. Other times, it's better to pull it up to become the exponent. And you want to do whatever makes your problem easier. All right, let's take a couple of sample problems and just work through those. These are the 3 basic laws that we're going to work with. And by the way, I've sent you a sheet showing a bunch of the logarithm rules. And here are 2 of them right here. Log xy equals log x plus log y. Log x over y equals log x minus log y. And then here's the conversion of, going back and forth. Like the log to the exponential form is log base b, the argument a equals x, becomes base, and then the exponent, logs are exponents, b to the x equals a. So I've sent you a copy of that, and you can keep that for reference on this homework. Let's do a couple of problems and see if we're catching on. And here's a little bit of a tricky one. If it asks you to evaluate log 1.5. Well, log of 1.5, we just don't know how to do that, do we? But, look, that's also equal to log 3 over 2. Well, that's going to be a little bit easier because that's equal to log 3 minus log 2. And you say, well, I don't really know how to evaluate those either. But at the beginning of your first homework assignment, there's a table which I've included in your copies there in the assignment, and it shows what log 3 and log 2 are. In fact, it shows all the way up to 10, and you can use that table then to determine, you just take the value of log 3 and subtract the value of log 2, and you can get it. So that is given, and that's how you would solve that particular problem, given the table that has log 1, 2, 3, 4, 5, 6, 7, 8, 9. All right, let's do another one. Let's say we have log 2 minus log 20. What would that be? Now, first of all, let's make this into a single log. So that's log 2 over 20. Well, that equals what? Log 1 over 10. Now, how do I evaluate log 1 over 10? We did this last time. I'm going to set it equal to x. Log 1 over 10 equals x. And then I'm going to convert it to exponential form. What's the base? 10. What's the exponent? Logs are exponents, 10 to the x. And that equals the argument then, so that's 1 over 10. Well, how can I solve this just without a calculator? 10 to the x equals 1/10. Well, 1/10, if you will remember, about negative exponents equals 10 to the negative 1. And here's a basic truth. If 10 to the x equals 10 to the negative 1, see they're both base 10, doesn't this x have to equal the negative 1? Yes, it does. So the original x back here equals the log 1/10. Log 1 over 10 equals a negative 1. Got it? All right, do another one. Let's take let's take 2 log 5 plus log 4 and analyze without a calculator what that's equal to. And when you're doing your homework, I need you to show me how you are doing this. Well, 2 log 5, remember when we have a number out front multiplied by the log, it's also the exponent? So this becomes log 5 squared plus log 4. Well, what's 5 squared? Isn't that 25? And what is this? Isn't this log 5 squared times 4? Remember, that's the basic rule of logs, that log of x plus log of y equals the log of x times y. And this is why logs were created, to simplify a multiplication problem into an addition problem. Well, 5 squared is 25 times 4. This is just equal to log 100. And how do I evaluate that? I set it equal to x. And I remember that it's a common log with a base 10. I convert it to exponential form. The base logs equal exponents equals 100. Folks, I think you know, what would x have to be to have 10 to the x equal 100? X is 2. So log of 100 equals 2. See how that's done? Pretty fancy, huh? All right, let's get, if we're given log A equals 4, and you're asked to convert that into the exponential form, how would we do that? What's the base? Base is 10. So I convert, and I've got 10 logs are exponents. 10 to the 4th equals A. Well, what's that? 10 to the 4th is 10,000. Piece of cake. Kind of fun. Hope you enjoy it. There's a lot of information in the attachments. Send me your stuff, and also send me a copy from last time of your graph of the logarithmic parent function along with the inverse exponential function that we talked in the last video. Thanks.